Yeah, there's one. Hey everyone, I'm Ben Feinstein. To my left here is my colleague Jeff Jarmoc. Appreciate you taking the time out and joining us. I know there's a couple other great talks going on right now, so thanks for coming in. I'm a little bit in danger of dating myself with a Rolling Stones reference. Maybe we should have used Justin Bieber or something more topical, but judging from the age of the people here, I think you guys would get this. And just to start with a picture of a thought about multi-tenancy in the public cloud. This is one way you can kind of conceive of a public cloud or a multi-tenant architecture, sort of a bazaar there. So what does this talk about? What we set out to do earlier this year is to do some research within Amazon's EC2 cloud, their public infrastructure cloud. We didn't decide to do this to pick on Amazon per se, but rather they're the market leader in terms of infrastructure clouds, and Amazon Web Services is definitely the biggest out there. So if you're going to do research in terms of a cloud platform, it's probably going to be done in Amazon's cloud. So what we set out to do is initially understand all the different types of credentials and that are used for Amazon Web Services. And as you'll find a little bit later as we go into those, AWS has really grown organically, so there's all sorts of different types of credentials and identifiers that you have to use as you're using Amazon's Web Services, and some of them are more powerful than others and give you control over other types of credentials. Once we had an understanding of sort of all these different credential types, we wanted to understand how users of Amazon's cloud services may inadvertently be exposing these credentials in their machine images. We'll be talking a little bit, defining some terminology here. Could I get a show of hands of people who've directly used some of Amazon's web services? So pretty big uptake. And who all here has actually created an Amazon machine image from scratch? Great, so we've got some people with some hands-on experience. Just bear with me as I do a little bit of definitions in a moment here. So what we also did is we wrote a tool that you can run against multiple Amazon machine images and look for these kind of credentials or backdoors or other risks that are inherent in those machine images. It also looks for some backdoors or things that may indicate that image is malicious. And then we also ran an experiment we'll talk about a little bit later to quantify the potential scale of victims if you were to release a malicious Amazon machine image into the public cloud. Before we set off on this investigation, we read up on Amazon's customer agreement, their terms of service, and all the stuff we did was consistent with our reading of that. And also throughout the process, we're working hands-on with their web services security team and notifying them of our findings, and then they were off doing customer notifications and taking actions when we found something troublesome. So to start off, why are people adopting the cloud? It's a buzzword. It's sort of trendy, for the past couple years here, but really it's just a tool. There's good uses for a tool, there's bad uses, and there's also suicidal uses out there. So you could think of it just like any other tool, like a knife, for example, in terms of the good, the bad, and the suicidal. In terms of the good uses of cloud and why are organizations adopting the cloud? One, it's to lower their cost of operations, to decrease their time to market, to be able to rapidly scale up or scale down their infrastructure at will, and also to get a geographically dispersed infrastructure without having to invest in physical data centers and infrastructure and things of that nature. In terms of a bad use of a tool or the bad uses of the cloud here, one is cyber criminals or attackers can use cloud infrastructure for relative anonymity. They're hiding behind Amazon's infrastructure and not having to stand up their own infrastructure. It's also can be free or almost no cost if you're someone who's using stolen credit cards or you've obtained Amazon credentials through other ways. And we'll talk a little bit about, in our research, the cost to someone to find an Amazon credential through using our tool to scan these machine images. It's very difficult for the defenders to just blacklist Amazon's net blocks. There's so many different organizations and applications that are using the net blocks that if you're just going to blacklist all of Amazon's IP space, you're probably going to break a lot of uses for your users and break a lot of your applications.
Well, and on that point, it used to be that you would see a lot of servers in the cloud. You wouldn't necessarily see client traffic originating there. I'm kind of interested to see how that new Kindle Fire and that Silk browser changes this, because now you're going to have client traffic originating from EC2, which kind of complicates that even further. You can't just just assume that it's going to be server side.
That's a great point, Jeff. With the Kindle Fire and the Silk browser, basically major websites are going to be seeing all their users popping out of Amazon's net blocks as they access their web applications. So another reason why just blacklisting web IP space from Amazon is not a real option here. Geographical disbursement, it's good and bad. In enterprise, it's a great thing, but also for criminals, if you want to be able to hop out of infrastructure in Asia and Europe and the United States or wherever, using Amazon's cloud is useful there. And also scalability. It's a good thing for enterprises and also can apply to cyber criminals or other attackers out there. If you look in the press, you Google around, you can see a lot of examples of this kind of activity, be it spammers using it. There was a version of the SpyEye Trojan horse that was using Amazon S3 object storage for drop site. People scanning for open SIP endpoints. I don't know if it was HDMore or not, but Amazon's IP space has definitely been used for this. And then going on the theme of the good, the bad, and the suicidal, what we're really talking about today is sort of the bad, but the suicidal uses of Amazon Web Services. What we found is it's very easy, or it was very easy, for people that are creating these Amazon machine images and then publishing them to inadvertently bake in private keys, credentials, identifiers, other data that they probably don't want out there, and then publish that image into the public cloud. So don't be this guy. Really, this is not about Amazon's failings or problems with Amazon's own systems. It's really showing how people need to be more careful and more thoughtful as they're publishing Amazon machine images, but also as they're using third-party AMIs out there. So looks like we have a pretty good crowd here of users of AWS. For those that aren't as familiar, when I say AWS, I'm talking about Amazon Web Services. That's a whole suite of different cloud services that they offer to their users. The EC2 is the Elastic Compute Cloud. That's basically an infrastructure as a service cloud. You can spin up virtual machines at will in any number of different regions around the world. And you're using Amazon shared infrastructure, networking, and storage with those EC2 instances. AMI, or I've also heard the Amazon guys pronounce it AMI, is their virtual appliance container format. It's just a file format that defines a virtual machine that you can launch instances of within their EC2 cloud. The simple storage service is object storage within Amazon's cloud. They call the storage units buckets, and you can read and write data objects into those buckets. And then the Elastic Block Store is essentially a cloud block device. If you're a Linux or Unix user, you could mount /dev HDA or whatever as a block device and read and write to that. Well, EBS, you create an EBS volume, and essentially it's a cloud block device that you can mount on any number of instances and read and write, and you pay by the number of thousands of I/O operations to that block device. Then this virtual cloud block device is basically replicated across all their infrastructure. So pretty powerful way to store data in the cloud with a very simple abstraction of just a block device.
Well, and it's important to note that it is a block device. It's not a file system. So that has implications when you when you delete files and things. Just like any file system, you delete a file, it'll remove the allocations, but the data is still there in those blocks. It can be recovered. It's been proven that deleted files can be recovered from EBS volumes.
So that's almost a whole nother talk there is cloud forensics, but yeah, Amazon's most recent guidance is around secure deletion. So if you just RM a file on this Elastic Block Store, that's really living on a series of SAN arrays across a series of data centers within their infrastructure, and it's essentially like unlinking a file, but that file is replicated across hard drives all over the place. So to talk a little bit about the credentials and look into the different types of credentials within use in Amazon Web Services, there's really three broad categories. One is access credentials. These are the keys and credentials you use to access different web services. A second is sign-on credentials or sign-in credentials. These are sort of the key to rule them all. If you obtain access to somebody's AWS sign-in credentials, you can pretty much do anything with their account at will. You can create new access credentials, manipulate access credentials. So this is the most sensitive set of credentials there. And then account identifiers. They're not directly, they don't directly give you access to the account, but it does identify the user and the organization that account belongs to. So in terms of the access keys, this is a type of credential that's an access credential. You'll see there's a key ID and there's a secret access key. It's essentially a public-private kind of key pair concept there. And then you use this for various web services APIs and SOAP APIs. As AWS sort of grew organically, some services use some sets of credentials, other services use others. In this case, their REST and query APIs use these credentials. Anybody used the Mechanical Turk before? In that case, it uses these. And then CloudFront is another web service they offer that uses these sets of credentials. And to Amazon's credit, they do have some security guidance around these, and they say, please rotate these credentials every 90 days at a minimum. And they've got a nifty web interface to manage these things. They also have some APIs you can use to manage it too in terms of scripting key rotation or scripting creation of these credentials. Another juicy target is X509 certificates. You use these for their SOAP APIs with the exception of S3 and Mechanical Turk. Again, there's a lot of complexity here as these things have grown organically, that certain web services and APIs use one thing and certain others use a whole other set of credentials. You can choose to have Amazon generate the private key on your behalf, or you could generate it on your own machine and then upload the public key part of it. But the interesting thing, these X509 certificate and private key pairs are used when you bundle an AMI or an Amazon machine image. So bundling is the process, it's the final step of creating a machine image, and basically it takes all the separate parts, bundles them into a manifest, and then splits that file up into buckets that then you can upload into S3. They're used to cryptographically sign that bundle, and if you're using it for a private AMI, it also will also encrypt the AMI bundle. Again, Amazon's recommendation is to rotate these things every 90 days. And another screenshot of a different web panel that you use to manipulate the certificates. EC2 key pairs. These are literally SSH key pairs. If you're familiar with accessing SSH servers using public key authentication, it's the same concept here. You generate a private key and public key pair using the RSA algorithm. You can do this within Amazon's web interface, or you can do it on your own. And when you launch an EC2 instance, you can load at runtime, at launch time, you can load the public key into the authorized keys file for the SSH daemon on that server, and then you will have the private key and be able to SSH into that device. It's important to note that eliminates the need to actually bake an authorized key file into the image itself, because that authorized keys file is propagated, or it's loaded when you launch the instance itself over a little cloud link local interface 169 so and such. And then you can actually run Windows images within EC2. And what they do for Windows images is they take the administrative remote desktop protocol password and they encrypt it with the private key. And so to get access to it, you have to decrypt that encrypted key, and then you can RDP right into your EC2 instance. And all this happens at the time you launch the instance. You don't have to bake in credentials into the AMI itself. And there's no explicit security recommendations around these. And another nifty web interface where you can manage these things. CloudFront, a whole nother set of credentials. Again, you can provide your own, or you can have them generate them on your behalf. They state that they don't store the private key. You just take them at their word for it. And then this is to generate signed URLs. In terms of CloudFront, it's a content distribution network. If you're familiar with Akamai, that's one of the leading CDNs out there. You can create signed URLs that are essentially links to private content within the content distribution network. And this is what the credentials are used for there. Now, the sign-in credentials, if you've ever purchased something from Amazon's online store, you already have a login to Amazon.com. It's your email address is your username, and then some password that you set. If you want to start using AWS, you essentially log right into their website and say, hey, I want to activate Amazon Web Services from my Amazon account. You're not creating a separate account. It's the same account you bought that book or you bought that CD on. They have some password complexity recommendations. As far as I can tell, they're not enforced. That may have changed, not certain. And then they also now offer multi-factor auth for these credentials. So for enterprises or organizations that are using cloud services for more than just research or science fair project kind of stuff, you probably ought to look at using the multi-factor auth solution they offer. Luckily, they did not pick Secure ID as their technology base here. They used another vendor. And we hear that they're still planning to roll out the LOLCAT retinal scan authentication mechanism in the near future. Account identifiers. Basically, these are there's different types of account identifiers. There's a canonical ID and a regular account ID. These are associated with images that are published to the public set of images in their clouds. And you use these IDs when you share resources with other accounts in the cloud. There's no public mapping of the identifier to the name of the organization, though some organizations that publish images as a course of business do make it obvious that, hey, 1, 2, 3, 4, 5 is actually RightScale or Cloudera or another vendor out there. When we went into working on this earlier this year, we found some prior research that had been done a couple years ago by Alex Stamos and some other researchers back at Black Hat 2009, DEFCON 17. They identified some interesting tricks you could do here. So I think in the US East Coast region, there's 7,000 or 8,000 public Amazon machine images that are out there. So the key is, if you want someone to use the AMI that you publish, you need to find a way to game the system and get prime search placement. So if someone looks for Ubuntu, or they look for a particular version of Fedora, if your machine image isn't in the top few search results there, no one's probably going to pick it. So they demonstrated a trick where you could repeatedly rebundle the image and get a new identifier, and eventually they did enough times where they get a very low number, and it was sorted by the Amazon machine image identifier. With that trick, they were able to publish, I won't say a backdoored image, but an image that would phone home to their server. And they basically demonstrated that yes, we can readily obtain victims by publishing a potentially malicious image out there.
Yeah, and there's other ways to do that too. I mean, you can just use some basic social engineering and just make an image that's attractive to your target user base, and hope that they run it. And we'll talk about that sort of thing a little more later.
And another thing that popped up back in April was on the Tipping Point DV Labs blog, they published this letter that Amazon's security team sent out to some of the users. And it turns out that a user going by the name Guru published a machine image, released it publicly, but he had baked his own authorized key into the image. And Amazon was notified, and they found quite a few organizations were running their infrastructure using this machine image. So the impact is basically whoever Guru was, presumably he had the private key pair, or the private key to this public key, and he could log right into the instances of any of these organizations and obtain access. So Amazon notified the customers that were running instances based on this AMI and recommended that they disable the offended key and migrate their infrastructure off of the image and pick a more trustworthy image in the future. So this really reinforced to us that this was a real problem. It was actually occurring in the real world. People were sharing machine images that already had authorized keys files baked into them, that presumably third parties can now obtain access to some organization's virtual infrastructure based on the fact they used the third party's AMI that they didn't quite vet closely. So we wanted to write some tools that would easily allow people to check for these kind of flaws, and that's what Jeff's going to talk about now.
All right, so another thing that came up as we were working on this, we were pretty far along in the project. We'd already been accepted to speak at DerbyCon and at DEF CON when a group in Germany of postdoctoral researchers released findings that were pretty similar to ours. They did a similar thing and did some large-scale scanning to identify images that were exposing keys and credential materials incorrectly. Their tool works a little bit differently than ours. They've got a Python script that they released that you run on the instance to scan it. I like our approach a little bit more just because I don't need to have a Python interpreter on the instance, and I don't need to run anything directly on the instance. I do it all over SSH. But it's just interesting to see that there's at least one other group that's working on this, and it kind of makes me wonder how many other people have done it and haven't gotten up on stage to talk about it. So with all these credentials and key materials and different things, it's pretty easy to screw up and leave them exposed accidentally. So when you're creating an AMI, you can leave these things on the file system of the image that you publish, essentially making your own key materials and credentials public for anybody who goes out there and looks. So we decided to look, several thousand times. So on the file system itself, you could have the AWS cert and private key, SSH key pairs. We've seen SSL certs and private keys, in public images. Within your bash history file, you may have command line environment variables that set some of these key materials for scripts to call them. And your bash profile might do the same thing. You've even got Vim info files that can show you the history of how the image files were edited prior to it being published. You might go into Vim and delete a line and think that it's gone, but then it's actually cached in Vim info. So if that's on the image, that could be another path.
I'll point out that this is actually a real book that's being sold in Amazon's bookstore, the Internet Password Notebook. It's a book to write all your internet passwords down and store next to your machine.
Yeah, the click to look inside is kind of a funny little touch there too. So there's a lot of signs that you can look for on these on these images to find when these things have happened. Obviously, you can have your authorized keys, and that's a pretty big finding. A lot of those are probably accidental, and we'll get into statistics later. But there's no way to know if there's an authorized key file there. Was the person who built the image just sloppy and left it there by mistake, or do they have the intent of later going back and trying to connect it to the image? When you're consuming a third-party image, it may well come with a rootkit or some sort of backdoor already installed. You can look for, you can try and identify active connections that are outbound to an unknown IP that might be some sort of backdoor connection in progress. And you can always Trojan the kernel directly. You can now run your own kernel on EC2. It's a little bit more complicated than using some of their provided kernels, but it can be done, and it's pretty powerful. So whoever publishes the AMI basically controls the entire state of the machine at the first boot. So you're putting a lot of trust in the provider when you consume a third-party AMI. So Ben already mentioned some of the work that had been done previously on evil AMIs or malicious AMIs. We did some other work to quantify this a little bit more, try and find out what the scale is, how many people could we potentially try and can we expect to compromise through publishing a malicious AMI. And then there's some interesting statistical things, not so much from a security perspective, but just in general, what regions are most popular, what size instances are people launching typically. And then the big question is really, are people using security groups correctly? And we'll talk more about security groups later. It's essentially a firewall policy for an EC2 instance that allows you to restrict inbound connections. So if you're smart and you only allow SSH from your own machine or from authorized administrative machines, those authorized keys aren't going to be much use. But we suspected and have some evidence that supports that people widely don't use those correctly. But getting back to the main initial part of the talk, we released a tool. It's out on the internet released under GPL. It's on SecureWorks website. I also put it up on GitHub. So it's GPL. You can browse the source tree. Feel free to use it, submit patches, whatever you'd like to do. But essentially, it's a framework that allows for bulk scanning of AMI images. So it uses Amazon's API to get a list of images that are within our scope, launch an instance of each image, connect to it over SSH, run a series of tests, and then record any findings to a database. So the tool is called AMI Exposed. So it's a little bit of a pun on the AMI moniker and asking a question, is this image potentially exposed with key materials and credentials? So there's 10 test modules included in the tool at release, and they look for things like the presence of SSH authorized keys. That could be a potential backdoor path. Are there SSH identity keys, the private key side of SSH? And we've found this in some cases where you'll have a private key that's used to authenticate to other hosts, not to the image itself, but in the process of building that, they were copying software over from another tool, from another host or something like that. We also look for the AWS X509 certificates. Once you have that certificate, as Ben said, you can pretty much do anything you want with the publisher's EC2 account. So that's a pretty valuable one. We look for active connections to other hosts that might indicate that there's a backdoor that's already got a session open to a third party. And then we look for, is SSH password authentication enabled? In a lot of cases, we find that despite the fact that Amazon's service is built pretty heavily around key authentication, some people will publish images with password authentication, and then that can expose you to default passwords that are included with the image, weak passwords, typical brute force attacks, and things like that. We also run some tests against various system files, primarily focusing on bash history, vim info, bash profile, bash RC, and then anything that's in etc profile D. So we look through, when we find these files, we iterate through all of them and look for various strings within them that generally are setting environment variables of the Amazon Web Service, access key, secret key, the canonical ID for S3, and then just the AWS account ID, because oftentimes that'll live nearby, other more interesting key materials that we may have missed. And we also look for some common environment variable names that are used to store these. A lot of the tools and scripts that Amazon provides and a lot of third-party scripts will look for things like, EC2 secret key, by default. So if you have EC2 secret key set in your profile, it'll find that key material and use it. So there's a handful of common environment variable names that can point to these. And so this slide kind of outlines the execution flow of the tool. So the first step there is to define the scope. So basically, there's a tool called tagimages.rb that's included in the AMI exposed. And this will query EC2 looking for all AMIs that match my scope. So the version that we have in there basically looks for, I'll get into that later. But basically, tag images automates finding images that match my criteria and tagging them within EC2 to just indicate that they're in scope. The next part of this is managing threads. We wanted to scan a lot of images quickly, so there's going to be some threading involved. So we need to query EC2 to retrieve that list of all our images that are in scope, and then iterate over the AMIs, creating a separate thread for each one. So I should mention this tool is written in Ruby. So we're using a lot of different gems through here, and we use a gem called threaded collections. It makes it real easy to do a typical Ruby each iterator, but then each iteration over that enumerable object becomes its own thread automatically. And then once we launch the instance, we have to do some work with SSH. So we have to figure out what SSH key is associated with that instance, and we do that through the EC2 API. We then need to determine, and I'm sorry, this is prior to launching. We need to determine what machine type and what size of instance we need for a given image. Some images require a 64-bit machine image, some require a 32-bit, some won't run on micros. So you need to take that into account and launch the appropriate instance. Once you launch the instance, you monitor the EC2 API, wait until that instance is in the running state. So throughout this process, we're using the AWS SDK. As I was writing this tool, I actually got pretty far into writing it using their SOAP API, and about 2 weeks before DerbyCon, Amazon released an official AWS SDK for Ruby. It's really nice, so I rewrote the whole tool 2 weeks before we released it and still had to do the whole scan. So I was a little bit stressed out about that because I took on a lot of additional work late in the game, but using that SDK is really a much more elegant approach, and I think makes for a better tool. So now that we have a running instance, we've got to try and SSH into it. So the first thing we do is try and log in as root. A lot of times, the root user is accepted. If the root user is not accepted, it's pretty common that you'll get a banner back that says, please log in as EC2 user, or please log in as Ubuntu. So we try and parse that username from the banner to determine what user account we need to log in under. If that fails, we just go through a dictionary attack, against 20 or so usernames that we've encountered in the wild. So for all the SSH connectivity, we're using the RubyNet SSH gem. And then once we have an instance, we can log into it over SSH. That's where our actual tests come into play. So we iterate through a list of test modules. Each module is a separate file. It kind of abstracts away all the SSH connectivity bits and makes for a pretty simple test module. It's almost similar to how Metasploit has different exploit modules, and they can all share common functionality from other classes. So we iterate through all our test modules, load each module, run that test, and then as there's any findings, we record them in the database. And that's done through the active record gem to make database backed objects. Okay, so I'm going to demo the tool. It takes a little while to run, so while it's running, I'm going to talk a little bit more about the internals.
So please pray to the demo gods.
Yeah.
It worked at DEF CON just fine, but we're sharing a wireless network with all the rest of the conference here, so please don't DOS us while we're doing this.
Okay, so that's up there. Put this in seamless. Okay, so let me first show you on the AWS console here, we've got 3 AMIs that I built. These are private AMIs. Well, actually one of them is public, but this AMI here is a public Backtrack 5 AMI that I released that we'll talk about a little bit later. The second one is one that while I was in the process of building the AMI, I mistakenly messed up how SSHD pulls its keys and things. So if I scan this AMI, I can't SSH to it because it doesn't properly load my key. So you'll note here that it's got a tag AMI exposed that's marked failed. That's from a previous run of the tool where it timed out because it couldn't SSH. And you see down here it's got a message that says timeout while getting user execution expired. This third one here is the DerbyCon demo. This is basically one that I just put a bunch of key materials in just to demonstrate the tool. So these two are marked as pending. That's how we define the scope, just basically a tag called AMI exposed that marks it as pending. So the tag images script goes through and looks for, as it ships, it looks for all public instances that are not Windows, that are not paid. I didn't want to deal with Windows images because you have to interact with them over RDP. It would have made the tool a lot more complex. And then the paid images, there's additional fees, and you need to authorize your account for them. It gets a little bit more complex, and we were also trying to reduce costs. But we've got 2 images here that are in scope. So if we go over to our SSH session, is that big enough for everybody? This is another instance that's running in the EC2 cloud right now that's hosting the tool. So this AMI exposed directory is basically the root of the application. So if I launch scan.rb, and I need to do ruby scan.rb, we get a banner starting up. It's telling me where it's putting its logs. So under logs/AMIs, it'll create a file with the AMI ID of each image that it scans that contains all the information about that particular AMI. And again, it also records everything to a database. So here it's starting a test of these 2 AMIs that it found were within scope. It's configured right now to use 13 threads. You can adjust the number of threads. Obviously, with only 2 images, it's not going to be scanning, it's not going to be using all 13. But this is going to take a few minutes to run. I just wanted to basically show that it's started. And we'll go back to the slides and come back to this in a few minutes to catch up with it.
So at the height of our experiment when we were scanning the entire US East region, how fast were we going?
Yeah, I got up to the point where I was doing about 150 images an hour. and that was with 13 threads. I needed to stay below the 20 concurrent instance limit. You can ask Amazon to increase your limit if you want to run more instances. I really didn't want to explain why I needed more instances. The Amazon security team knew what we were doing, but I kind of thought it might be a difficult conversation with whoever answers the phone when you call them to ask for additional capacity. So I just stayed within that limit, and that was kind of the threshold on how fast we could scan. At some points, I also encountered some rate limiting by the API, so I had to slow myself down a little bit because I was hitting their API harder than they like. So let's get back to the slides. Okay. So let's talk a little bit about some of the internals of the tool. It's using the AWS SDK really heavily. I talked about that. And basically, I'm just expanding. I'm opening up the existing classes within the SDK and adding my own functionality to them. So the first class that we had to modify was instance RB. This is basically a class that defines the object that represents each Amazon Web Service instance. So I added a method called getUser that finds the SSH username by checking to see if that user gets a shell by parsing the user from the banner or just by brute forcing the username. Then I added a run command option that basically just runs a command via SSH exec. There's also a run command PTY. Some commands require that you have a virtual terminal attached, and they won't run properly otherwise under an SSH exec. So we handle both cases. And then there's an instance run test method that takes a test file as an argument and runs that test against the instance. And then there's just a general run test that runs all tests that are located in the appropriate directory. Within the image class, we added an image test method. Basically, that runs a test against an AMI rather than an instance, but it does that by creating an instance that gets spun up and determining the SSH credentials and calling instance run tests. So it's basically a convenience method that makes it interact as if I'm scanning the AMI itself, when really I'm taking that AMI, spinning up an instance, connecting to it, and scanning that instance. So this tool could easily be modified to scan individual instances as well as images. So if you're concerned about materials that are in a running instance, you could do that as well. There's an SSH user attribute that I added as a tag on the image. So as I determine what the SSH username is, I just store that as a tag that's associated with that image, so that if I run it again, I don't have to go back and repeat all that. And then there's a test status attribute that updates the tag on EC2, so I can watch the tag change as images are scanned. And then there's a couple other classes. These are new classes that are implemented just by this tool. There's a finding class that uses active record, just basically to store findings to the database. And then there's a test class. So the initial test.rb file implements a class called base test. Base test is basically a parent class of the individual tests. So all the common functionality that all tests are going to need is stored here. There's a create finding method that you can, from the test, create a finding. And then there's a file helper module, and that's used by tests that look within those system files. So that file helper module has a number of regexes that are searched against each of those files, and those are defined within the config YAML file. So you can tweak the regex matches without ever modifying the test. All you need to do is modify the config file. And then there's our individual tests. So the individual tests implement a test class that descends from the base test class. There's an init method that basically just defines metadata about that test. What's its name? What sort of findings does it look for, etc. And then there's a run method that runs the test. So because we've had so much inheritance and there's so much abstracted from the other class, these test modules end up being pretty simple, and you can create them without having to worry too much about what's actually going on under the hood. So here's an example. This is a test file that that looks for bash history files and searches within that bash history file for any regex matches that are defined in the YAML file. So if it finds one, it'll log a finding. It's pretty simple. What was that, 30 lines? Here's another one that looks for SSH authorized keys. So we're looking at the SSH authorized key file and then searching within that file for any keys that exist that don't match the key that was provided by the Amazon Web Service API. So those would be third-party keys that were present, prior to the image being launched. Here's a little more complicated one. This one looks for active connections. So it basically does a netstat, looks for any connections that are established, and then does some regex to parse out various IPs and things from those, and then compares those to a whitelisted list of IP addresses that are in the config file. So things like my own SSH session don't show up. So let's talk about the scope of the testing that we did. We started out with all US East images that were available at the time that we were running this. Removed the Windows images from the scope, and we're left with 5,515 images in US East. So that's all non-Windows images. Am I Exposed processed all of those and found that 771 of them were paid images, so it just basically skipped those. So that left us with 4,744 images in our scope. As we tried to test those, we were kind of surprised to discover that 2,767 of them were not testable. Primarily, this is because they had errors in the image and they wouldn't launch. Common things included, some misconfigurations where the boot volume wasn't found. Maybe there was a kernel panic on boot. Somebody was trying to run a custom kernel and didn't have the appropriate Xen options compiled in. Missing manifest files in the case of S3 backed images, or as I showed with my other image, SSHD didn't start or wasn't configured correctly. So I was kind of surprised to see that there were so many broken images out there publicly. When you're building an image, it's pretty easy to break it, especially the first couple of times you do it. But it's surprising that people would mark these public. One thing that occurred to me is in the case of EBS images, you may still be able to mount the EBS volume despite the fact that the image won't boot. So while I didn't do it in this round of tests, I think it'd be interesting to go back and try and access these images that we couldn't actually boot by mounting the volume and scanning that volume. Because if they're broken already, I'm kind of assuming that the person who built them and made them public probably doesn't have a real good idea what they're doing, and there might be some juicy stuff here that we didn't find. So at the end of the project, we were left with 1,977 images that we had completed successfully. I mentioned the group of German researchers that did different work. The statistics they released, they said were based on 1,000 images, so we've got nearly twice as many. Of those images, we had 580 that had at least one finding. So that's 29.34% of the AMIs that we were able to successfully scan. Which is a pretty surprising number, I think. The German group said that they had approximately 30% that had issues, so we're in the same ballpark. I don't know what the scope of their test was, what region they tested, or really when they completed it. These things come and go, so it's hard to say how comparable our numbers are, but we're certainly within the same ballpark.
So as we were identifying these images that had findings in them, we were feeding that back to Amazon Web Services security team. Behind the scenes, they were doing customer notifications of both the publisher of the images, but also any customers of theirs that were found to be running instances based on these images. They're in a bit of a conundrum here because they can't just go shut down all the instances based on a problematic AMI image. This is somebody's infrastructure. This could be important applications or whatnot. So essentially, they have to notify the customer and say, we really strongly recommend that you migrate your applications onto instances based on another AMI, and then contact the publisher and say, hey, would you be so kind as to remove this image from the public list of images? So they were doing a lot of notifications behind the scenes. And the other important point is that when we found credentials or private keys or whatnot, we never attempted to utilize these, to validate these, or attempt to access any systems using the credentials that we found.
So there's also kind of two classes of exposures. There's exposures that put the publisher at risk, and there's exposures that put the consumer at risk. Something that puts the publisher at risk might be leaking their own Amazon keys. Something that puts the consumer at risk would be something like pre-existing authorized keys allowing third parties access. But we found both in pretty good numbers.
Should we check the results? You think it's ready?
Let me just get these,
right.
these next two and then we'll go back. So to summarize our findings, the largest one was the SSH authorized key issue. In our test, we found 386 images that had unknown SSH keys. So that's 19.52% of the images that we tested, and it represented 44.96% of all our findings. So this is really a big problem, and it's hard to say whether there was malicious intent here or whether it was people who just didn't know what they were doing and left those keys there. But as a consumer of an image, it doesn't much matter because my risk is the same. Whether or not somebody comes along and tries to access it, they could. And then here's a table listing our findings overall. There's a lot of data here, and we don't really have time to go through all of it. But you see the unauthorized SSH keys at the top. The history file, that was a big one too. A lot of these images came with bash history files. Further on down, we see SSH identity key files, and that kind of goes along with the history files. I mentioned earlier, if you have the identity key, you have the history file. A lot of times the history file will have previous connections that were used, that use that private key. And I found that in a couple of cases. So presumably, unless that key's been revoked or something, I now have the SSH private key and I know what host it belongs to. So it'd be pretty easy to get on that host. In the middle there, we've got our various AWS environment variables and keys. And further down, we have some of our other findings that came in lower numbers. At the bottom there, we've got SSH password authentication enabled, second from the bottom. There's a star next to that. I didn't add that test until we were partway through the run. So that actually didn't run on the complete, number of tests. But we found it in at least a couple of cases. Let me go back to the demo and see. I know we're running on time. Come on. Okay, so we can see here our test completed. The console log here is pretty, it doesn't give a lot of information because when you're scanning a lot of images, this scrolls really fast. But if we go into log AMIs, we've got our two logs there. So let's take a look at one of these. The 04B. So this one here came up pretty clean. You see at the top there were some timeouts trying to SSH. We had to add the SSH key as authorized. We were able to get the username, ran all these tests, and it really didn't find anything. So that one's clean. If we look at the other one, however, we see, well, let me more this. We see a whole bunch of findings. So it starts out roughly the same, gets the SSH username, runs these tests. Here's an example where I found an authorized SSH key. We scroll down, there's some other things here. This one's kind of interesting, and we'll talk about this later, but within bash history, we found some AWS key identifiers. I'll explain why that one's there later. And here's some other environment variables using EC2 keys, etc. If we go up to database, and this is just a SQLite database, we can just do select star from findings and see that all of those are recorded in the database as well. So that's basically how the tool operates. Let me get back to the slides. We're running a little tight on time, so I'm going to have to pick up the pace a bit. Okay, so how much did this cost us? When we're spinning up these instances, we incurred some fees, and it was $1,336.16 to test the entire U.S. East region. I actually asked Amazon if I could overpay $3.84 so that we could give them a check for $1,337, but they wouldn't let me do that. So it breaks down to 67 cents per image scanned, 98 cents per finding, $15.68 per Amazon Web Service credential. So for the cost of going to the movies, I can own somebody's Amazon Web Service account and use it for whatever purposes. If we had looked a little bit more manually into some of these findings, we may have found more things. We could have lowered our costs by using spot instances to take advantage of off-peak pricing. Again, I mentioned the analyzing the EBS images. That could have increased our scope. It could have reduced costs because we wouldn't have had to launch an instance. And then obviously if we were malicious, we would only have had to have done this until we found that first AWS credential. Then we could have hopped on that account and used that for the rest of it at somebody else's expense. So that would obviously reduce costs if somebody, we're looking to do this maliciously. So the question arises, in regards to the SSH key issue, don't most people use security groups to restrict SSH and, kind of negate the value of that possible vulnerability? So I mentioned before, EC2 groups are like firewall policies, essentially. There's some key differences. You can't change them unless you restart the instance. So that's kind of a restriction that encourages loose policies. If there's a possibility I'm going to need to add other source IPs that have access on a given port, I may not want to do that because I'd incur an outage to restart that instance. So I might just make a broader policy. There's no way to review logs to see what's been blocked, what's been allowed. So that's kind of a problem. I think a lot of the value of firewalls and filtering policies comes from the logging that they give you, as much or more than from the blocking and allowing. And the big thing here is these are only inbound. You can't set up filters for outbound traffic unless you're on Amazon's virtual private cloud. So exfiltration, phone home connections, connectbacks, no problem. If it's running on the instance connecting outbound, there's nothing there, other than maybe IP tables. But again, on the first boot, the image provider controls what executes on that box. So if the image provider didn't put an IP tables outbound filtering policy, you don't have one. So we wanted to do some testing of security group practices. I mentioned before this Backtrack 5 image that I released back in June. I'm in the process of working on a Backtrack 5 R1 image, so if anybody finds that interesting, hopefully it'll be out soon. Announced this publicly on Twitter, the Backtrack forums, IRC, SANS, GPON mailing list. This is the sort of thing that could be useful to pen testers, other folks that are interested in security, students. It's kind of handy to be able to run Backtrack in the cloud. And in our purpose, it was useful for gathering statistics. And you might be wondering how we got those statistics, because generally you don't have any information that comes back to you when somebody launches your image. So this AMI had a phone home in it. Everybody who launched that instance ran a bash script that was in varlib cloud scripts per boot phone home sh. On every boot, that would collect information about the instance via Amazon's metadata API. So it collected the instance ID, image ID, availability zone, etc. We intentionally stayed away from getting the SSH public key. Public key, by definition, shouldn't be all that sensitive, but I didn't want to get into anything that was personally identifiable, so we stayed away from that. So here's the script. It's pretty simple. There's a get meta function that grabs stuff from the metadata, and then curl just posts it back to my web server. So I was also curious how many people would find this. It's a pretty simple phone home that shouldn't be all that hard to find. I left a comment in there that said, hey, if you have questions, you found this, hit my website. I was going to credit people who found it, but nobody contacted me. So if anyone found this, I don't know about it. So it's kind of interesting. I don't say that because it was such a great, hidden backdoor that nobody found. It was pretty blatant. The script was named phone home.
It was using the standard cloud init mechanism, so it wasn't sneaky. Basically, it's just part of a standard AMI startup script.
So some statistics on this. We had 95 phone homes as of late July. 69 of those came from unique instance IDs, so the others were instances being rebooted themselves. I could actually tell when an instance was rebooted, if it was rebooted from within the guest OS, if it was rebooted from the the Amazon service, or if it was a brand new instance. So when we got a phone home, we tried to just pull an SSH banner from that box. We didn't try to log into SSH. We didn't leave any keys on there, so we weren't able to. But the fact that we're able to pull a banner indicates that SSH isn't filtered by the security group. And in 68 cases, we were able to connect back on port 22. So that's 71.5%. If you look at your unique instances, we had 50 unique instances that we were able to connect to, so kind of deduplicating those ones that were rebooted multiple times. And we come up with 72%. So largely, people are allowing SSH into their instances from at least our source, presumably from the entire internet. And I think it's interesting that this is a backtrack image. I would think that would appeal to a more security-minded audience, right? I realize a lot of times it's students, people who are interested but maybe not too skillful. But I would certainly think that this audience would be a little bit more security-minded. If we had left an SSH key on the instance, and remember that was our largest finding from scanning public images, we would have been able to compromise the vast majority of these. I imagine some people would have found an SSH key, but probably the majority of them we would have had. I think it's probably safe to say that the general populace of less security-minded folks may be in worse shape. More sophisticated backdoors would be even harder to detect. So when you're using a public AMI, you're really putting a lot of trust in the provider of that image. And that's important. I think most of us wouldn't go out to BitTorrent and download installation media and build enterprise applications on it. You're essentially doing the same thing if you're using public images. You need to know who's providing that, what their intentions are, and you probably want to audit these yourself to verify that they're secure. You want to take this?
Yeah, we got like 1 minute left. So a key part here is that Amazon's published a wealth of really strong guidance out there. You ought to go check it out. We've included some links. While we were working on this project, they went off and published some good guides, best practices guidance on how to use these things in a secure manner, how to share and use public AMIs. Elastic.com from Eric Hammond is a bunch of great material out there. Go check it out about AWS EC2 and the security of it. And then just recently, a few weeks ago, Amazon consolidated all this guidance, published this new document that we link here. And the coolest thing, though, is they just released a new revision of the bundle volume tool, which you use to bundle up AMIs, and now it will no longer include any of these kind of files that were the problem files, unless you explicitly tell the tool to include them in the image. So that, one, it eliminates unintentional exposure, and two, anytime you find, say, an SSH authorized keys file within an image, you know someone put it there intentionally. They had to override the tool, pass -- include, and pass the authorized keys file to the tool when they bundled it.
Yeah, and that change to their bundling tool came after our DEF CON presentation. So it's not confirmed that it's a direct result, but clearly it's it probably spurred some action. And
so the AWS security team was great to work with. They're very responsive. They investigate every report. Easy to get a hold of. Check out the URL. And then also, so where do you obtain trustworthy AMIs? Amazon publishes a whole bunch of them. They have their own Yum repository running in the cloud, so you can keep it patched and up to date very easily. Probably the best practices, we've talked to some big organizations that use this, is to start with an official Amazon AMI and then build an application-specific AMI on top of it. And just to wrap up, wanted to thank Beetle and the rest of the Amazon Web Services security team as we work through this project. Thank Dave and Martin and Iron Geek Adrian for throwing this great event, but especially all the volunteers that made DerbyCon possible. Really excited to be able to participate in the first year of this event, and I think it's going to be great and many more years to go. Thanks for your time.